All right, hey everyone, welcome back to today's first lecture. Giacomo will basically follow up on lecture Monday and talk about two hires, static quantum flow, and so on.
So thanks a lot. Also to all of you for being here this morning. So yeah, basically I want to kind of like take on and move forward from where we stopped last time. And last time, in the previous lecture, we kind of like I introduced the laws of thermodynamics in open quantum systems. I hope you kind of like remember the take-home messages like the entropy production, the first law, and so on. And I just want to say that, like, as I mentioned last time, like the laws of thermodynamics actually only apply when basically, I mean, they refer to average values, right? And they kind of like are the most meaningful thing to describe transformation between states when you kind of like talk about macroscopic systems where fluctuations become negligible due to the law of large numbers, okay? But whenever instead now in this lecture, we will move away from this kind of like setup and kind of investigate what happens out of equilibrium, okay? So beyond the laws of thermodynamics. And this becomes extremely relevant whenever well, you have a microscopic, like mesoscale or microscopic system, okay? It's where fluctuations become as important as the average values, and you have to include the higher statistics into basically what how do you analyze the performance of like machines or processes as well. So why, like, I mean, what I mean by fluctuations is basically when, for example, just as an example, if we reconsider the classical example that we had considered last time, the kind of like two-terminal double quantum dots scenario where one has like a double quantum dots that acts as a junction system between like two fermionic reservoir, okay? Essentially, if one has a way to measure kind of like the number of particles going through the system, like the particle current, which is also known as the power output, the power yield of this device, thermoelectric device, one would basically be able to see something like this popping up, okay? I prepared this time, I'm prepared. I'm too bad at drawing, so I just ran some some plots. This is just a random thing where essentially, as I was mentioning, like this can be, for example, the power, the electrical power that we defined last time. And what I mean is, like, after a transient time, okay, when the system reaches a sort of like non-equilibrium steady state that supports constant currents, basically the fluctuating current, which is this, I don't know if you can see the colors, the gray kind of wobbly curve, kind of like settles around like a dashed line, which is the average value, the average power, okay? And around which it oscillates, okay? According to like, and these are, for example, the fluctuations, okay? Like the kind of the variance of the power, like how broad is the power distributed around this average value, okay? And it's intuitive that even like from a layman perspective, that large fluctuation in any, like in the power output of this machine would be bad, okay? Because if I want this device to power something, then having large fluctuation means that this affects the reliability of your device, right? Because on one cycle or at some point in time, it may produce something much more than the power output and fry the chip, for example, or like much less, and it will be not enough like to actually power the chip. So basically, fluctuation, that is to say, the take-home message is that in the microscopic case, where fluctuations are not negligible with respect to the average values, so they don't become like very, very small, basically this fluctuation can impact the performance of your machines, of your devices, okay? And the desiderata, what we would like to want in principle, is to basically squash this fluctuation down as much as possible, okay? Like reduce the fluctuation, i.e. increase the precision. The concept of precision is this, like, is the reliability of the fluctuations, basically, of the process, okay? However, unfortunately, well, in nature, there is no free lunch anywhere, essentially. So if also in this case, like, for example, for the laws of thermodynamics, where we can never like extract work because of the second law of thermodynamics dictated on average, here also there is no free lunch, in the sense that if you want to reduce this fluctuation, you have to spend more, okay? You have to spend some resources, invest some resources into it. And if basically the quantity that you want to increase the precision of is a thermodynamic quantity, like the power, the heat current, and so on, those resources will be like in terms of energetic resources, like dissipated heat, dissipated work, and in general, like increase the irreversibility, the dissipation, like the amount of resources that you have to irreversibly spend, okay, and that you cannot get back, like in the same kind of fashion as the second law, but just to reduce, to increase the precision of the process, okay? So in some sense, it's also intuitive. The message is that it's intuitive that reducing fluctuation costs in terms of entropy production, okay? This was kind of like the leitmotiv that basically represented sort of like the overarching kind of goal and theme of research of the development of stochastic thermodynamics throughout basically since its conception and throughout its development. And I have prepared a sort of timeline that I know Jake loves, so I put it here as well. And well, basically, what does it say? That basically, okay, starting from the laws of thermodynamics, these were kind of like proven to be valid on average. And on the basically in the beginning of the 20th century, people like Gibbs, Boltzmann, like these superheroes of physics, essentially kind of like discover that everything like the thermodynamics is an emergent theory from like a stochastic description, like a stochastic model, and started to realize that all like thermodynamic quantities that are process dependent quantities, okay, they depend on the process, they are functions of the process, and since the process is stochastic, all the thermodynamic quantities becomes functions of the stochastic process and are stochastic functions, okay? And as I said, like understanding, like characterizing the like some universal properties of fluctuations out of equilibrium, and characterizing like the precise relationship between fluctuation on one end and dissipation on the other, like the cost for this fluctuation, okay, has been the theme basically throughout this timeline since today, and it's still an ongoing process, okay? And the first kind of like milestone result in this kind of like endeavor is the so-called fluctuation dissipation theorem by Green, Kubo, and Onsager, which basically can be kind of like in a layman statement can be cast into saying that if you take like a closed system and which starts initially in an equilibrium state, which we saw last time, okay, like a Gibbs state, for example, and you drive it out of equilibrium by, I don't know, like kicking it, okay? If the kick is like a perturbation, okay, which is the so-called linear response regime, then basically the fluctuations in the work that you see in the work distributions are proportional, directly proportional to the dissipation, okay? So if you wanna kind of like increase, so if you increase the dissipation, you increase the fluctuations and so on, okay, in this regime only. But it was not until like the 1990s, let's say mid 1990s, where these here two gentlemen, Christopher Jarzynski and Gavin Crooks, which I think are kind of like the forefathers of stochastic thermodynamics, modern theory, essentially. They discovered what are basically, I think, the most important result in so far in stochastic thermo when it comes to like characterizing properties of out of equilibrium fluctuations and processes. And these results are called the detailed fluctuation relation, which is this one, or fluctuation theorem. Also, it's not a theorem, okay. And the integral fluctuation relation, okay, here. And these basically apply arbitrarily far from equilibrium. They are not restricted like the fluctuation, the FDT, to linear response regime. They are valid arbitrarily out of equilibrium, and they can characterize properties like this one is a symmetry, a symmetry constraint on the probability distribution itself, okay, out of equilibrium. And this one is like a sort of like average of basically dissipation, okay. And but okay, despite their kind of like generality and a lot of things that can be said, like for example the the fluctuation relation FR, they have been used like in chemistry, for example, to kind of like calculate the free energy potential, which is an equilibrium quantity, just by like studying, calculating this average, like running some experiments randomly on like tweezers on DNA strands, basically calculating the work, just energy as the energy difference in what you do, and just like repeating this kind of process for like arbitrary kind of operations and protocols, and then calculating that average. And even though this is like a non-equilibrium process, then this actually can be used to compute like an equilibrium quantity, which has a lot of like importance for chemistry, okay? But the last result, which is like the third milestone in this kind of timeline, is the so-called thermodynamic uncertainty relation, or TUR, or TUR from now on, which were discovered by Barato and Seifert in 2015, and that go under this name TUR, because they kind of like are a sort of like uncertainty relation that involves like the first and second moment of the distribution of any thermodynamic quantity. Here, just for consistency, I selected the work, but it can be any thermodynamic quantity in terms of the dissipation, okay? And basically, what I want to say is that in this lecture, we are going to see, I'm going to present you like two possible derivations of this thermodynamic uncertainty relation. And I'm definitely not following the historical development, because the first like way to prove and derive this TUR are, I mean, for me at least, it's a very contrived way. It uses like large deviation theory, actually some results called level 2.5 large deviation theory, which I admit I don't understand clearly today. But like the thing is that there have been more recent derivations that are actually even more general than this, and I'm going to present two possible ways to derive this. But before doing that, I would like to basically give you a sort of like overview on what the standard TUR says, because I mean all TURs kind of can be kind of broadly stated as that if you have any kind of process gamma, okay, and you have a quantity that is a kind of like a process dependent quantity, like for example, a thermodynamic quantity, let's call it Q of gamma, okay, under some properties, but the TUR says that the kind of the noise to signal ratio of this quantity, okay, which is this quantity, this adimensional ratio, okay? So it's the ratio between the noise and the signal, okay? This is always greater or equal than a function of the average entropy production associated with the process, okay? And in the original formulation, this was 2 over sigma, okay? And why is this important? What does this bound tell us, okay? This bound. Well, it's telling us that if one wants to increase the precision, okay, on the left-hand side, that quantity, that noise to signal ratio can be interpreted as the precision. It's the relative precision, if you think about the example that we had, associated with a thermodynamic quantity Q, okay? And on the right-hand side, you have dissipation, okay? You have the entropy production, okay? And it says that if you want to increase the precision of any thermodynamic quantity along the process, then you have inevitably to spend more dissipation, okay? So you have to spend more resources to make the process more precise, okay? This kind of like goes in the spirit that we want, no? That we kind of like predicted intuitively. But perhaps the most kind of like important or interesting application of this TUR, like for like I would say practical reasons in the thermodynamic sense, was discovered in 2017 again by Seifert and Piazzonka, another collaborator of him, which is basically how this TUR, what this TUR imply for basically the performance of steady-state heat engines. Okay. And I want to kind of like show you this because I think it's a kind of like cool motivation to, and it explains a little bit of the hype around like beside the fundamental kind of importance and kind of like how cool they are like from a fundamental point of view, but also what I said. No, I mean that imagine that you have the same like 2 terminal setup, and for simplicity, let's like model this as we did at the very beginning, no, of thermodynamics, no, of the first lecture. So you have the system, you have the hot bath, and you have the cold bath, and kind of like the energy kind of flows this way. So you have a heat current here, J hot, a heat current, J cold, and you also do some work. Okay, no, actually you want to extract, if you want this to work as an engine, you want to extract work out of this heat, basically coming in from the hot bath towards the cold bath, okay? And if you remember at the very beginning of the first lecture, we characterized the performance of this steady state heat engine by calculating the ratio between the power output, or like the work per cycle, let's do work per cycle, divided by the current Okay, let's do this way. Sorry, let's introduce the quantities per cycle because we are at steady state, so we can do this. I've introduced already the current. Okay, so it's the ratio between the power I can extract on respect to the heat that basically goes into the system. Okay, and we found that the second law of thermodynamics kind of constrains this to be less or equal than the Carnot efficiency, no, which was a function like 1 minus T cold over the T hot. Okay. And basically also the second law of thermodynamics, if you remember, if you input in the explicit expression of the entropy production, said that if you you have a trade-off, like the second law imposes a trade-off that says like, if you want to achieve Carnot efficiency, okay, then you have to run the process like reversibly and have zero entropy production or zero power, but this means also zero power output, okay? So basically, and on the other hand, if you want to have a finite power output out of your engine, that this means running the process irreversibly in finite time and having an efficiency which is less than Carnot. Okay, so there is this kind of like trade-off dictated by the second law of thermodynamics, therefore on average, between the average power output and the maximum achievable efficiency, okay, of the engine. However, kind of like this, this statement was challenged in 2015 by Michele Campisi and Saro Fazio, who basically wrote, studied an engine where, like a microscopic engine where this system here in the middle, making the junction, basically was a critical system, like a series of n qubits in a critical point, okay? And they were able to show that running the analysis of this, they were able to show that it was possible to achieve Carnot efficiency at finite power output, no? And seemingly violating the second law of thermodynamics. And this was kind of like made the news a little bit. This was like, okay, did we achieve like the holy grail of perpetuum mobile? And the answer is no. Okay, this actually hinted at something more profound, like at the real role of fluctuations in this kind of system. And why is that? It's because basically TUR, when applied to this setup, actually provide the elegant answer to this problem. And to realize that is that basically take the TUR I just showed you above, okay, and specialize it to one particular thermodynamic quantity, meaning the work, okay? So basically in this setup, as I said, the power is the limit in the kind of the steady state of the work divided by T, okay? It's 1 over T, the average work. And the fluctuations also become linear in time, okay? So it's limit T equals to infinity of the variance of the work divided by T. And likewise, the kind of the entropy is constantly produced because there's a constant current. So basically you can introduce the entropy production rate as the limit for T that goes to infinity of the sigma divided by T. And if you basically then use these three quantities in and you plug it there, you immediately get that the TUR translate into the following bound, okay? Greater or equal than 2 over sigma. And why is this like, what is this telling us? Well, let's use the two laws of thermodynamics here. At steady state, you have that basically these were J hot plus J cold plus the power, okay? And this at steady state, it's 0, okay? And the second law of thermodynamics said that sigma was minus J hot divided by T hot minus J cold divided by T cold plus delta S, well, ds, which again, the S being 0 at steady state, okay? The change in the system entropy, okay? So rearranging these two, essentially to basically use this to substitute in like sigma, basically, I mean, this is a very simple calculation, but essentially if you use this equation, you can rewrite sigma as P over the temperature of the cold bath times 1 minus the ratio between the Carnot efficiency and the real efficiency, okay? And if you substitute now this expression for the entropy production in the TUR here, okay, what you get is essentially the following upper bound on the maximum extractable power from this engine, from this microscopic engine, which explicitly takes into account and includes the power fluctuations, so the precision of the engine. That looks like this. And this is the, and as you can see here, okay, what is this telling us, this new upper bound? This new upper bound is telling us, if you look at it, that it's actually possible to achieve Carnot efficiency at finite power output. So have that quantity going to zero, but still have a non-zero left-hand side. How? Using diverging fluctuations. Okay, so if the fluctuation, the variance of the power, diverge as one, eta c over eta minus 1 to the minus 1, okay, so as the inverse of what's going to zero essentially, then this quantity stays finite, equal to 1 over 2c. Okay, so as you can see, this is exactly what happens with an engine at a critical point, because at the critical point, as you surely know, fluctuations diverge. Okay, the second derivative diverge and so on, right? So basically, it's true that like if you stick the analysis to the average values, you may be kind of tempted to say, oh, I found like an engine that has finite power output at Carnot efficiency. But its reliability, so the analysis of its fluctuation reveals that its reliability is zero. Okay, the fluctuations diverge, and therefore like it's completely useless. Okay. Yeah. Any question before I proceed, or everything is clear? Take it as a yes, which is good. Okay, so this kind of like sort of like concludes the motivation. And well, I mean, kind of this spurred. So the original TUR with the bound as 2 over sigma were originally discovered in like for systems that were actually like steady state Markov chains. So Markov chains. Do you remember hopefully the lecture by Gabriel in the first day? Okay, like classical systems. Okay, that are a graph of vertices and transitions, okay, between vertices, and basically, if this process is brought to the steady state and satisfies detailed balance, you know, the ratio between the forward and backward transition are like thermal in a Boltzmann factor, essentially, then you can show that this applies, like these 2 over sigma apply, okay, this bound. However, like, I mean, as you surely know, I mean, like having a Markov, like a system, like classical system described by a Markov chain at steady state regime with detailed balance is not the most general scenario that you may think of, right? I mean, so there's a lot of like assumptions and words to explain it, no? So basically, because of this hype, this is also applicable to engines that can be mapped onto such models, okay? So it's still in that regime. People just got into like wondering, okay, but what happens if I like kind of relax this assumption? Do I still find this TUR valid? I mean, are they universal? Is this like kind of like highlighting a sort of like fundamental trade-off bound like the second law of thermodynamics, which does not depend on the process, okay? And well, the answer was yes, TUR apply almost generally. I mean, generally with an asterisk so far. I have only seen very few examples where they seem to be arbitrarily violated. But the thing is that the standard TUR can be violated. Okay, there are generalized TUR, so there is still a trade-off of the form that we mentioned, which is the variance of like a quantity divided by the average square greater or equal than a function of the average entropy production. Okay, of course, like the left-hand side is always greater or equal than 0. So the meaningful thing would be to just get something which is like something positive, okay, here on the right-hand side. But the point is that it's possible to violate them, no? And there are like 2 main big ways to violate TURs. The first one is by kind of like externally driving the system, okay, with a non-time reversal symmetric protocol. So, but this comes at a cost, because like driving the system costs kind of like additional resources, okay? And so it makes sense that you can violate the standard TUR if you like put more energy or put more resources into it. And the second kind of like more interesting from my point of view way to derive this is actually using genuine quantum effects. Okay, so like deviating from the classical Markov chain at steady state by introducing, I don't know, like coherences or entanglement or a phenomenon called quantum friction that I'm not sure you have heard of, but you may stop me later and I will tell you in detail because I don't have time to go into this. But it's basically the generation of instantaneous coherences. It's basically when you drive a system out of equilibrium, you drive something in time, okay, Hamiltonian. You can drive the eigenvalues, no, but at fixed basis, or you can drive also the basis and only in the quantum case can the H dot not commute with H, clearly, no? If you rotate the basis. And this is a genuine quantum effect called quantum friction, okay? So these are like two kind of like big main categories. And in kind of like most of these scenarios, there's a lot of ongoing research in that field. But the point is that people have found generalized TOR that valid that take into account for this kind of other scenarios, okay? And I will be kind of like discussing two of the possible ways. Would have liked to like also include more, but kind of like I had to cut at some point. Okay, so let's start with kind of like the first one, and the first kind of like way to that they chose to kind of like show here to derive TOR is as they kind of like stem from the fluctuation relation. Okay, because if we go 1 second back to the timeline, it kind of like, as the second law of thermodynamics is a consequence of, and the fluctuation dissipation theorem can be seen as a consequence of the fluctuation theorem that kind of like involve the full probability distribution, one would be tempted, okay, or I was kind of like wondering, could anyone derive TORs, okay, from this kind of like symmetry on the whole distribution? And the answer is positive, okay, but it's like the result that you get is a kind of like different form, okay, of TOR. Sorry. So okay, so basically the setup I have in mind I've chosen is a bit non-standard, but it's also a cute thing that it's called like repeated interaction scheme or collisional model. I know some of you have worked with collisional models. Actually, there are experts in the, like Stefano, for example. But the thing is that it's a game, okay? So bear with me, okay? And so the game I have in mind is the following. Imagine that, or maybe I have a picture of this I've prepared, so I don't have to draw it again. That would be amazing. Yes. Okay. Cool. So it's the following. Okay. So instead of kind of like the basic framework I kind of like showed you last time, okay, where you had a reduced system rho s that interacts with like an environment, the latter also being the possible like collection of heat paths, or like that you call environment, whatever, like the surrounding thing. You actually substitute this thing with the thing on the right. What is this? This is like my best attempt to draw like a conveyor belt thing, okay, to kind of like indicate that this kind of open quantum system scenario is mapped onto like the stroboscopic repeated interaction scheme, okay, where kind of like the system rho s now doesn't interact with rho e, but interacts with like an auxiliary system rho a for a finite amount of time tau, okay. Then after they interact, basically this ancillary system is like trashed. That's the bin there. And the new ancilla arrives, interacts for another time tau, it's trashed, and so on and so forth, okay? And this repeated interaction scheme is a very, very powerful method to simulate open quantum system dynamics, okay? This is the simplest kind of like memoryless version of the collisional model or repeated interaction scheme, but you can also like include like non-Markovianity effect in the first picture by including like, for example, non-negligible interactions between the ancillas and so on. I mean, you can play a more complicated game, which is out of the purpose for the moment. But the point is like that what we have in mind for our game is that we have a finite dimensional system. Okay, finite dimensional system described by rho s of t, okay, and an Hamiltonian which might be time dependent, not externally time dependent. Lambda of t was the working protocol, okay, was the set of instructions given by the experimentalist, like to kind of like change from the external the parameters of the Hamiltonian, like the magnetic field or whatever, okay. And then you have n copies of this auxiliary system that are all identical and non-interacting with each other, okay? So basically this means that the Hamiltonian of the environment, okay, is can be written as the direct sum, like the sum of HA of Hamiltonians of the ancillas. They do not interact with each other, and these are considered assumed to be time independent, no? As in the open quantum system scenario, where you assume that you don't have control over the environment. Okay, and before basically the interaction, so with the system, all the initial state of the whole environment is then the tensor product of these n ancillas, rho a's, where all rho a's are assumed, in my case, to be a thermal state at temperature beta. Okay, so they basically, and why is this? Because we want to do thermodynamics, so we want to kind of like throw in something thermal, some equilibrium state somewhere. Okay, instead of having a thermal equilibrium state for the environment, we kind of like have a collection of thermal small ancilla. Okay. I don't have at this point to specify what is the system interaction between, like the real form between the system and interaction. But if you want to be kind of precise, you can say that the system environment original kind of interaction can now be written as kind of alpha from 1 to n of theta of basically, well, of let's do it like this, of a system ancilla interaction, which is switched on at n tau, sorry, this is n, and switched off n plus 1 tau. Okay, this is like a heavy side theta, so it's a sort of like interaction that it's switched on at n theta. Okay, you got it. Okay, switched on, top hat function. Okay, and as I said, after each interaction, so we want to also play the following game. We want to also keep track of the energy change. Okay, and what does it mean is that we don't just like make the system and ancilla interact and then trash away the ancilla, but we also want to measure like the energy of both the system and ancilla before and after each interaction. Okay, because we want to keep track of this. Okay, so after each interaction and before, I should have said before and after, but okay, a projective measurement of HA and HS is performed. Then the ancilla is discarded. And what does it mean? It means that you do a partial trace over the ancilla. Okay, this means discarding it. Okay, tracing over its degrees of freedom, and then a new one is brought in. Okay, so the system is updated after every step. Okay, but the ancilla, it's like a fresh, identical new one at each step. Okay, and therefore, if you imagine to remove the measurement, okay, the measurement part, this is called repeating interaction scheme, because if no measurements are performed, then the state of the system after, let's say, n times tau, tau being the interaction time, okay, is just given by the application of a map, a CPTP map that we kind of introduced last time, repeated n times, okay, stroboscopically, applied to rho s of 0. And what is the explicit form of lambda, okay, of tau? This is the partial trace over the ancilla of the system ancilla unitary evolution, okay? So USA. Rho s 0, yeah. This is tensor product, right? That joke was not intended. Okay, right? And then, yeah. All right, so, but what happens if we measure like the observables, okay? So, well, what happens is the following. Imagine, so now you want to play this game and you want to characterize what is called as the forward process, okay? And I'm going to explain why I'm calling this the forward process. So you want to start by measuring an observable, okay? I already said that it's going to be the Hamiltonian of the system, okay? But just for generality, let's call it X, okay? It can be any, because I want to stress that it can be any observable. as long as the initial state of the system, as I'm gonna say in a second, commute with that observable you wanna measure, you can play the same game, okay? So for the moment, bear with me. And I know the notation for now, from now on, is gonna be a bit ugly, okay? But I promise you I will walk you through it. And it's not gonna be more difficult than me jumping in the sea yesterday, so it's okay. So basically we wanna measure the observable X, okay, which is gonna be driven over time, and which is gonna have the spectral decomposition, spectral representation given by some of the eigenvalues time projectors, okay? I'm using notions that you have seen in the talk in the lecture by Anya, okay? So I hope you are familiar, but please, with these concepts, but please stop me if something is not clear, okay? And also an observable of the ancilla Y, which has the same, since it's a self-adjoint operator, it has the spectral representation like this, okay? These projectors, just using a Dirac notation, is something like x0, x0, okay? Something like that, right? And the initial state, as I said, is rho SA 0. It's the kind of like uncorrelated state like this, okay? Where we assume that rho S of 0 commutes with H0 and rho A commutes with Y, okay? What does it mean? It means that I'm staying general because I want to look cool, but okay, like this, if x0 is the system energy and y is the energy, is the Hamiltonian of the ancilla, this, for example, means that the system starts in an energy eigenstate, for example, and the ancilla starts in a thermal state. Okay, they both commute with them. So this means that if I do a projective measurement, I'm selecting one basically eigenstate of the, for example, if I start from a thermal state, I select one possible eigenstate, for example, with probability given by the Boltzmann factor, but I'm not destroying any coherence. I'm not changing the state dramatically, okay? That's what I mean. Okay, so yeah, the system plus ancilla evolved unitarily. Sorry, this means that rho S0 can be written as sum over x0 of some weights, okay? Let's call this like that, times the same projectors, right? And rho A can be written as sum over y of EAY times the projectors, okay? So they can be written on the same basis, okay? Times some weights. Okay, so finally, I mean, as I said, this unitary operator is actually something that depends on the protocol lambda, okay, that I'm doing from the external, okay, and in particular, like the u lambda of t0 is the t exponential that we saw last time, blah blah blah, okay. Oops. Of hs plus ha plus hsa of t. Okay, same thing. I'm going to be fast on this. Okay, and what happens? Okay, bear with me. So you measure these two observables, okay, and imagine that out of these measurements you record two outcomes. You get two numbers, okay, and you call these numbers that you got. Imagine something like I don't know, x0i and yi, okay, for the system and for the environment, and you keep them as a data point, no, using the words that Gabriel used. Okay, this is a first data point. Okay, the two measurement outcomes. Then essentially what happens is that after the measurement, okay, you're going to have a conditional state conditioned on these projective measurements on the outcome, okay? And this state, so if you call this data point, I don't know, V naught, okay, V naught is this kind of like 2D vector, okay? Then the state becomes rho 0 conditioned on V0, which is nothing but the projector on V0 applied to rho SA of 0. This was SA. V0 divided by the trace of whatever comes at the numerator, okay? Just for normalizations, okay? Cool. And in particular, just to be clear, I mean, this becomes like, since if we use this kind of expressions here, this becomes this guy, okay, times the projector, tensor product, PAYI, tensor product, right? This is the post-measurement state, okay? And this is evolved. If you look at what happens here, this is evolved up to time tau, okay? And you get, after the evolution, joint evolution, you get the state rho at time tau conditioned onto the measurement outcome V0 again, okay? Which is just U lambda tau 0, rho 0 condition on V0, U dagger lambda of T0, right? And then you do a second measurement of the same observables, which in this case are going to be x of tau, because we can assume that this observable could be changed over time, okay? Which kind of has this kind of eigenvalues, x tau pi of x tau. And you measure also the variable, the observable y, which, however, this one does not depend on time, I repeat, okay? Because it's from the environment. It's the observable that belongs to the environment you don't have control over time on, okay? And now imagine that as a result of this second projective measurement, okay, you get two other outcomes, two other numbers, okay? And you call them x tau final and y final, okay? And you call this V1, something like that, okay? So clear? Please stop me, like, if, or raise the hand, if yes.
You leave the equation longer.
Sure. Maybe I can also like zoom out. That might help. Thank you. And if I'm going too fast, like, let me know. Okay, so just to summarize, the thing is I have two data points, okay, out of this kind of elementary process, okay? The first one is V0, and the second one is V1. They are two numbers, okay? And if I repeat the same kind of thought experiment, this like basic building block many times, okay, I will get each time, each run, I will get a different V0 and a different V1, okay? And therefore, this is a process called two-point measurement scheme, okay? This kind of like measure, evolution, measure, okay? It's called the two-point measurement scheme, and it represents kind of like the Lego building block of basically the repeated interaction scheme. The repeated interaction scheme that we're gonna build in a second will be just kind of like doing this n times, okay? And getting, instead of two data points, getting n data points, okay? But like, I want you to understand that even like this 2PM scheme, okay, gives you the full statistics, okay, in principle. It's called full counting statistics for this reason, because if you then, like, for example, at this point, you construct the variable delta V, okay, defined as V1 minus V0, like the difference in the outcomes that you obtained, okay, this, upon repetition of the experiment, this quantity becomes a random variable, okay? You get the difference between two numbers that are classical data points that are like randomly distributed, okay? And if you do this many times, this kind of delta V will move from an histogram to like a probability distribution, no? P of delta V. And this basically is how you construct, for example, the probability distribution of the energy change in the system, which you interpret as work, okay? The probability of work distribution, and so on and so forth. So from this probability distribution, you can construct like the average work standard way. You basically, for example, if delta V is the delta energy change, okay? The change like in the total eigenvalues of the energy, if you measure the energy, then essentially you can get the nth moment of the work, and you construct this P of delta E, okay? by repeating the experiment, this thought experiment many times, then you can, in principle, kind of like reconstruct this as delta E, P of delta E, and then multiplying that by delta E to the end, no? Because it's a random variable, right? Actually, the best way to basically then get these moments of the work distribution, heat distribution, whatever you want, depending on what you measure, is actually to go to the Fourier space of the probability distribution, okay? Like do the Fourier transform, and basically get this, go to the, it's a classical thing, it's so well known, it's the generating function. It's called like that because, I mean, the nth moment is the nth power of the probability distribution, like of the variable delta E, but like this becomes the nth derivative in the Fourier space, no? So it becomes much more easy, and one can show, but this is out of the purpose of this lecture, so I'm not gonna do this. But the thing is that the cool part about the full counting statistics is that this generating function, okay, can be rewritten as the trace of the operator, like the final conditioned operator, okay? So if you run this experiment, you calculate somehow the trace of that operator, like you do tomography, whatever, I don't know. Then you get immediately, depending on what you measure at the beginning, at the end, you get the statistics of that observable, which is cool. Okay, but okay, we don't care about that for the moment, for the present lecture. What we want is that, so I want to say that the joint probability, coming back, the joint probability of having recorded V0 at time 0 and V1 at time tau, okay, 1 times tau, for me that's the notation, is given by the Born rule, okay, standard. So it's P of V1 and V0, okay, it's just a trace of what? Of the project. So you start, let's do it this way. Let's start from the initial state. You project it onto the eigenvalue V0. You evolve it up to time tau. Okay. And then you project it onto the eigenspace V1. Okay. This is the joint probability distribution of having these two, having obtained these two outcomes. Right? And it's a proper probability distribution. It sums to 1, that's like its marginals are well defined, and so on and so forth. Now, what we want to do, as I said, is that we take this kind of like 2-point measurement scheme and we do it n times, okay? But with one kind of, we have to be precise about something, is that essentially after each single of these 2 PM scheme, you need to trace out and trash the ancilla, okay? And at the beginning of the initial state of the subsequent evolution, okay, it's gonna be the same state of the system times a new freshly prepared ancilla, okay? What does it mean? It means that if I had, for example, like obtained like the eigenvalues, let's say at the final state, the final V1, okay, V1 was something like x1 I and or j, let's call it j, and yj, okay, for example. No, let's call it y. I like it. X1 I and yy. That was not good. Anyway, very good choice. But the thing is that this kind of like means that the initial state of the subsequent evolution, okay, of the subsequent collision is going to be essentially the state which is xi1, xi1, okay, this projector for the part of the system, tensor product rho a new fresh rho a, okay? And what does it mean? It means that if I then restart and do the same measurement of x and y, okay, I will obtain for sure the same eigenvalue xy of 1 on the part of the system because of the orthogonality of projectors, no? If I start from one eigenstate and I measure anything, no, either I get 0 or I get that eigenvalue, okay? So the kind of like the V2, okay, which is the first measurement of the following ancilla, it's bound to be xi1 for the system. But in principle, since I brought in a new ancilla, I can get a different eigenvalue for the ancilla yj, okay? And what did it mean? It means that I had a transition from I to j in the path, in the environment, okay? And this is going to become important, okay? Because essentially this means that if I had this measurement, okay, then then it means that after n times of this, I'm gonna have basically, and I will have collected a series of outcomes, okay, that are gonna be like an n times 2-dimensional vector, okay, a vector of data points, n-dimensional if I do n times this thing, which I call gamma, okay, which will look like this: x0i. I'm just randomly giving names to these points: x, j, tau, y, j1. Okay, this is for the first measurement. Okay, and then I will have x, j, tau, the same times y, I2, x, k, 2 tau, y, j2, and so on and so forth until the very end, which is the last point at the last end interaction, which is, I don't know, some x n minus tau, and finally x, what I call final, because I like y, j, n. Okay, and we call this gamma a trajectory. Okay. Why a trajectory? Because it's a collection of data points connected by an underlying dynamics, okay? And they are like classical data points. So it's meaningful to call them trajectory. And if you put all things together, like the probability to observe such trajectory is gonna be given by P of gamma, which is basically the joint probability distribution of having V0, V1, and so on until the last point, the last data point, okay? V is the double. Okay, which is gonna be basically given by the trace of, I'm gonna explain what this notation mean in a second. P1, U1, P0 times the weights, like which are PS of x0y, which was basically the weight of the first initial state, okay? Afterwards, it was always projected, so it had no weight. And then, however, all the weights of the initial and ancillas, okay? So PA of YIK, okay? This is the first result that I want you to remember. It's the probability to observe this trajectory, all right? And what is this notation? This notation is this calligraphic P of index k is just the projection onto Vk of rho. Okay, it's a shorthand notation. It means that it acts on the left and on the right of the argument. Okay, and Uk, this calligraphic U applied to rho is basically just the evolution operator. Okay, from k tau to k minus 1 tau. Like that, the Kate collision essentially, okay? Sorry, this is lambda. All right. You still following me so far? Like, is everything clear about the forward process? Any question? No? Yes?
Thanks. Really quickly, where is rho in that highlighted expression?
I kind of like, so there was like a small triple dot here, like a passage. So I did one passage, I did not write. It should be here on the left, here. Should be here. but like I used the fact that, so it's written in these weights, essentially. I kind of like wrote rho, the initial rho, okay, as the initial weight times the projector, and then I use the idempotency, I guess it's called, of the projector. So that's that was the passage. I have written all the passages in the notes, but due to the lack of time, I was like giving you the results. But thanks for spotting this.
Right, those are the PS and PA.
Yes, and I want you to notice that while the weight of the system only enters at the beginning, okay, because you never kind of refresh the system, okay, so you only have a different than one weight at the beginning, and then it's projector, 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 so there's no weight. At the ancilla, because you refresh the ancilla at each point, you always have like n weights entering here, okay, and this is important, because the system is going to be like a sort of like initial and final kind of endpoint quantity at the end. While that one, the one on the environment, will keep track of the process on the between things. Okay, thanks a lot. Okay, so I don't know what I did. Okay, so why did I call this thing that we did the forward process? Who can guess? Because there's going to be a backward one. Okay, and why do I wanna torture you with the backward process? Well, I mean, there is a good reason to do so. And the good reason is that in thermodynamics, the second law dictates, I mean, the irreversibility, the notion of irreversibility, which is basically connected to the notion of directionality of time. It's what gives the directionality to time, okay, to the parameter that governs the evolution, okay, is basically the notion of this irreversibility is something that, loosely speaking, is refers to the comparison between a process and its time reversal. Okay, so if everything is reversible, I do something and I do it backwards and I get to the same initial point, right? Because it's reversible, as the name suggests. If it's irreversible, so if there is entropy production, it means that this irreversibility means that if I start a process somewhere, I do my forward process, and then I basically turn backward the time and end the kind of like instruction, the external protocol that I give, I don't end up in the initial starting point. No, this is the irreversibility. So since I wanna kind of like introduce this notion of irreversibility at the level of the trajectories, okay, I wanna introduce the reverse trajectory and then compare them. Okay, cool. So in order to do so, to kind of introduce the backward process, the first thing I have to introduce is the so-called time reversal operator. Okay, it's the operator that basically gives the flips the signs of like magnetic fields and so on. No, right? It's the thing that you must have seen somewhere in the quantum mechanics course, I hope. So it's basically an operator which for some reason historically it's denoted with this capital theta. I don't know why. Which is an anti-unitary operator. It's called the time reversal operator. Wait, sorry. Yeah, the time reversal operator is the time reversal operator, and is anti-unitary, meaning that and satisfies the properties that theta times I is minus I theta, okay, and theta minus 1 is equal to theta minus 1 theta is equal to the identity, and therefore theta minus 1 is the adjoint. Okay, anyway, what is the kind of the action of this operator is basically it reverses the sign, changes the sign of like odd variables under time reversal, like magnetic field, like momentum, and so on and so forth, and leaves everything else like position invariant. Okay, cool. And like if you have a system and an environment, like a composite structure, like system and ancilla in our case, okay, theta is something like theta SA, it's theta S tensor product theta 8. Like you have to invert both the system and the ancilla like observables. Okay, And what we want to do is basically revert both the evolution and the measurements. Okay, you want to measure the reversed observable and basically revert the protocol and revert the evolution and then measure the final reverted observable. Like you want to revert everything in time. Okay, if you want to do things properly. So basically, it means that if I had first measured an observable A, okay, which was something like, I don't know, had this spectral decomposition, no, where A was either X or Y in general, okay, and the notation before, then I will denote with the tilde sign the time reversed observable, which is theta times A times theta, okay, dagger, okay, and because of the properties of the time reversal operator, this does not change the eigenvalues, okay, of the observable. This is quite very easy to prove, but it will, in principle, change the eigenvectors. Okay, it's like think about, if you struggle with this, think about like measuring momentum or something. No, you have to kind of flip the sign. For example, if you want to measure the backward velocity of a car, like the time reversal. Okay. Cool. And then like the initial state that I want to choose, okay, to start my backward process, start the backward process with rho as a tilde initial, okay, which is gonna be basically the time reversed end state, no, of the forward. So I want to kind of like arrive at the final state of the forward process and then start from there and revert things, okay, to compare their reversibility, to quantify their reversibility. So this is going to be the kind of the time reversal operator on the system, if I want to be pedantic, times basically rho s x final and tau, what I call like that, times its projector, okay, x final and tau, x final and tau, tensor product, theta A times PA, what I called JN, I guess it was, JN, theta A, there. All right, all clear, right? Because why there are no correlations? Because I did trash the last ancilla, so I destroyed the correlations, okay? But cool. And then I do the same game, no? At the same game, but with the reverse things now. But it's the same thing. So essentially, one starts the stroboscopic game as before, but one needs to pay attention because basically the reversed dynamics, okay, evolves according to the operator. So like in between the each two measurements, okay, the reverse dynamics is given by between the system and ancilla by the tilde lambda operator, okay, which also is referred to the reversed protocol. Okay, I'm gonna explain to you in a second what I mean by this. So it's the kind of like the t exponential, okay, of the integral over t of basically a time reversed Hamiltonian, okay. And what is this lambda? Okay, the lambda was the driving protocol, was the list of instructions that the experimental. Yes. Do you know the state of the ancilla at the end? Yes, I had recorded the weights. You remember? So I kind of like I can re-prepare the state by just like I imagine to be able to kind of be able to prepare us an ancilla in that state in some sense, if that makes sense. I hope. Like I mean, I had the number, like the Boltzmann factor of the thermal state, and therefore, like I imagine to be able to prepare an eigenstate with that Boltzmann factor, if you want. What I mean by like the backward, like the sort of like reversed process, is that this. So imagine that I want that satisfies this kind of like this symmetry here. What does it mean? It means the following, okay? So I have prepared this nice figure here, which kind of shows that basically you want like to do the kind of like the time reversed protocol, okay? If you drive things kind of like externally, what you have to do is like if you had a time protocol lambda t, like a list of instruction from 0 to t, okay? This must at any point coincide with basically the list of reverse instruction that basically take the system from the final time tau back to t again, okay? So that's symmetry. So at any point, the two things must do the same operation, okay, from the external. Is it clear? Is this clear? Hopefully the kind of the graphic kind of explains this a little bit better. Okay. Fine. So I'm gonna not like bother you too much with like repeating everything I just said for the forward process, but like the game, imagine that the game is the same, no? So you had this initial state, you do the projective measurements of the reversed observable, you record the outcomes, okay? You evolve, you measure recording the outcome, re-prepare the ancilla, and so on and so forth. And you get a collection again of numbers, of data points. No, the same, okay? But they refer to this kind of like reverse trajectory, okay? And in principle, they can be completely different. But if you run like several millions of times this forward and backward, you're going to have a collection of data points referring to a forward process and a collection of data points referring to backward processes, okay? And if you repeat this game enough times, okay, you're going to have that for each trajectory, for each forward trajectory, okay, gamma, you're going to have an associated backward trajectory, which is basically kind of like the data points backwards, the same data points, but backwards, okay? It's just like, it has to happen, right? So basically, how to say this, like so should I write this or was it clear? Like, so basically for every trajectory, forward trajectory gamma, there exist. What are these explosions, by the way? I heard them yesterday too. Is it like a festival or something? Huh. Okay. A conjugate reverse trajectory gamma tilde, okay, which is observed with probability p tilde of gamma tilde, which is basically ps of x final pa of jk, and then the trace of p0, un, p1, until u1 tilde pn. You may notice here that essentially you have the u tilde instead of the u's, okay, and that the order of the projectors are the other way, okay. So first I had on the most right hand side, I had originally in the forward the p0, and the last one was pn, and here it's the opposite, okay. And the other kind of like difference, okay, is here the weights, they refer to the final state j, not the I before. So if the transition in the forward observed on the ancilla was from I to j, okay, from the final state and then you re-prepare was I to j. In this case, in the backward is from j to I, okay. So before you had yik and now yjk, okay, referring to this transition. So these are the weights of the reverse transition. This is becoming important. Okay. And there's only a few steps remaining because now basically I have the two probability distributions of the forward and of the backward trajectory. And I can introduce a quantity, which I call sigma of gamma, which is just the log of the ratio of these two probabilities. Okay, and this is called stochastic entropy production. Or stochastic irreversibility. However, in order to kind of like really compute this and really kind of like quantify the distance between these two probability distribution, I still need one last element, which is the so-called, it's stemming from the micro reversibility principle. The micro reversibility principle is basically what will allow us to connect U tilde, okay, with U dagger in some sense, with the reversed original dynamics. And what is the micro reversibility principle? From micro reversibility, okay, which tells essentially that the underlying microscopic equation of motions are invariant under time reversal. This is very well known. Okay, the Hamiltonian equations are symmetric under time reversal. Okay, the irreversibility is an emergent phenomenon. Okay, but microscopically, everything is reversal, time reversal. So this means that the micro reversibility means that the Hamiltonian under time reversal doesn't change, or that it commutes with the time reversal operator. Okay, and it can be shown, okay, that this implies, there are a few passages, but this implies that the U tilde, like the generator, okay, of the evolution in the reverse process from k tau to k minus 1, from k minus 1 tau to k tau of the basically the Kate collision is this one, n minus k plus 1 tau, n minus k tau times theta minus theta dagger. Sorry. Okay, is it clear? Okay, this is like, I mean, it's clear. I mean, it's like that. I mean, I don't expect you to see why this is the case, because it's like it requires a little bit of passages, but like, so basically it means that it's related to the fact that basically I can change the protocol, and the Kate collision in the reverse is the final n collision minus k1 in the forward, okay? And then I have to revert basically in that step, I have to revert things, okay? Using the micro reversibility. All in all, if I basically then use this relation, I plug it here, okay, in the expression of p tilde, of gamma tilde, then, and I simplify stuff, I arrive at the desired expression for the stochastic entropy production, which is gonna read quite simple actually, and it will look like this, times the and then final n tau times k1 and p a y j k. Okay, and so basically just a ratio of the weights that were appearing in front, like everything that goes inside the trace simplifies essentially, which is a huge simplification, no? And then we are left with just kind of these numbers, which you can also split a little bit more, because these two numbers refer, sorry, these two numbers here refers to the system, and these numbers here refer to the ancillas, okay? And I can use the logarithms properties to write this as log of ps x y over ps x final and tau, okay? Plus the sum over all the collisions, okay, of log of pa yjk, sorry, ak, divided by yjk. And what are these? This is the so-called system stochastic entropy and the environment stochastic entropy. In the stochastic entropy of system, and this is the stochastic entropy of the environment, like the collection of ancillas. Okay. This result, okay, this expression is the so-called detailed fluctuation relation by Crookes. And it's very, I think it's incredibly beautiful, because essentially, why did I call, for example, this quantity, this first term here, why is it like a stochastic version of the system entropy? Okay, because basically, if you think, like if you compute, for example, like the average of this, okay, so this the trajectory average, so delta S gamma, okay, of the system, right? So this becomes the von Neumann entropy. So rho S of n tau minus rho S of 0. Cool, no? Like this is, if you think about it, no? I mean, the trace of rho log rho, okay, it's the expectation value of log rho, no? Expectation value of log rho. And this is exactly it, no? So it's the log rho initial minus log rho final, this one, no? And so this is like on average gives you the phenomenon, the change in the von Neumann entropy of the system. And the second term is the change in the von Neumann entropy of the environment, which if you start like we did, if the ancillas, if rho A's are thermal states, okay, so tau of beta, then it means that these weights here are the Boltzmann weights, okay? So the various PA of, for example, J1, okay, is E2 minus beta epsilon J1 minus delta F, no? The Boltzmann factor. And then if you substitute these guys here, right, then the stochastic entropy of the environment along the trajectory is just the sum over the various collisions of beta times ejk minus eik. Okay, so the sum of the changes in the energies of the ancillas. Okay, and if you remember the definition of the heat was if the bath was started in a canonical state, in a thermal state, okay, the change in the energies of the bath was the heat. Do you remember? So this is beta times Q, like the heat defined on the trajectory. It's pretty cool. And the last thing I want to say about this is that from the detailed fluctuation relation, okay, one can immediately integrate. So consider E2 the exponential of this guy, okay, of E2 minus the entropy production, the stochastic entropy production. Calculate the average. Okay, what is this? This is explicitly the sum over all possible trajectories of the probability for the trajectories times this stochastic factor. Okay, and this is what? P of gamma, and then P tilde of gamma tilde divided by P of gamma. These two simplify. The sum over gamma is equal to the sum over gamma tilde. Okay, because the sum over gamma means the sum over all possible data points, but gamma tilde was just the same data points in reverse, so the sum is the same, and this is 1 because it's a probability distribution. So you get this famous result, which is the integral fluctuation relation. Okay, it's super cool, no? Okay, but the point is, where I want to arrive is, how much time do I have left? Because we started 20 minutes late, so 10 minutes, okay. So I'm not sure I will be able to say everything, but like the point is that so we were wondering. So this is like the fluctuation relation, no, the celebrated fluctuation relation, like the one by, if you remember the timeline by Jarzynski and Crookes, okay, in the fully quantum setup that we studied. But now the question is, can a TUR, a relation on the signal to noise ratio of the quantities X and Y that we measure, like the energy, for example, can this be derived from the symmetry? And the answer is that, okay, in general, it's still kind of an open problem. But if you kind of like impose an additional constraint, like for a subclass of this fluctuation relation, it's possible, okay? And this is the so-called TUR from fluctuation relation. And in the sub case where essentially, if we assume that the probability, okay, the p tilde of gamma tilde of the backward trajectory is the same probability of gamma tilde, okay? So you don't have two different probability distribution. The probability distribution itself is the same, okay? This is a subcategory of fluctuation relation that holds valid either when you are in a steady state, in a non-equilibrium steady state, because basically the time reversed is mostly the same, or if you do like a driving which is cyclical, so the final point is basically equal to the initial point. You can understand why the probability is the same. In these two cases, then it's possible to derive a TUR. We were able to show that it's possible to derive a TUR from this symmetry on the probability distribution, okay? And to see this, so assume I consider basically a thermodynamic integrated current. And let's call this like, I don't know, Z of gamma, okay, a function of the trajectory, which is like, I don't know, the heat, the work, whatever, okay? And it's a function of the stochastic trajectory, okay? And we assume that it's anti-symmetric, okay? So which is anti-symmetric under time reversal. Meaning that Z calculated on the backward trajectory is minus Z along the forward. Like, for example, the heat current, no? It's a sort of like speed. It's a momentum-ish, observable, okay? It has a directionality. If I revert the process, it has to change, it changes the sign. That's what it means, okay? Then basically, by the way, like also the entropy production, if you revert the things, changes sign. So that's one example of the observable that we want. And we assume that the joint probability distribution, assume that the joint distribution to observe a stochastic entropy production, sorry, a stochastic entropy production sigma, okay, sigma of gamma. Sorry, like that. Let's do it like this. And some value for the observable Z, let's call it Z gamma, okay, is given by P of Z and sigma, which is the sum over all possible gammas of kind of like the probability of gamma here, and then kind of like sigma minus sigma gamma, delta of Z minus Z gamma, right? Simple. It's like two functions. And basically one noticed that if it satisfies the exchange fluctuation theorem, that kind of like symmetry that that I told you, meaning that basically P of gamma is equal to P of gamma tilde times E2 sigma. This becomes the exchange fluctuation relation. This you can write as this one. You can write as this. Okay. All right. So much kind of like in the spirit of the James principle, basically when one wanted to find the minimum bias state compatible with a set of constraints given by the expectation values of a given set of observable, we aim here to answer to the following kind of like question. We aim like for fixed average sigma observed and fixed average Z, okay, such that the probability distribution satisfies this symmetry. what is the minimum value for the precision? Sorry, the maximum value for the precision, the minimum value for the variance. And what we obtain is that one can derive a tour answering this question that it's a bit hard to prove, but which means that we call the tour de force. This theorem is in the paper that basically it says that for fixed values of Z and sigma, okay, the probability distribution, joint probability distribution that's compatible with the symmetry Pz sigma equal to P minus Z minus sigma e to sigma with the smallest possible variance is given by a kind of like two direct delta distribution, which it's like it has a rather horrible form. Actually, let me okay. Well, yeah, I don't know if I have the time to write all this stuff, but let's say it's like a sum of two direct deltas. It's a weird distribution with basically positions dictated by A and B's that are constant by fixed by the averages, like constraints, like the Lagrange multipliers in James' principle that we saw last time, like this. And Z is equal to B and half. And this means that basically for any other probability, different, I mean, yeah, that's so if you take like this minimal probability distribution, the variance is going to be minimum. But if you take any other probability distribution, so for any other P of Z and sigma, then it means that the variance of Z divided by Z squared is going to be greater or equal than F of sigma, with F of X being this weird looking horrible function. And okay, I mean, G being the inverse of the hyperbolic tangent, whatever. I mean, the point is that like this kind of like horrible looking function has a sort of like shape like this, where X is this, F of X is this, and it kind of like goes like this, okay? And the point is it relates to the 2 over X original bound, which looks like this, because if you expand F of X around 0, you get 2 over X minus a constant alpha in some sense, okay? So for small dissipation, you still get the original TUR, but then you get like corrections, okay? Just as like a result of this fluctuation relation. So there actually is a way to derive this result in a much simpler and possibly more elegant way, which I will give you in the notes. It only takes like a page, although like the one that, or a couple of pages, although we kind of, and by the way, it stems from Cauchy-Schwarz inequality, unsurprisingly. But the thing is that like in the paper, don't look at the demonstration of this because it was a bit hard to follow. But in any case, it kind of like uses convexity properties and the Cauchy-Schwarz inequality. Okay, but you can show this in full generality. Now I don't have any time left, or do I? Because the point is that what I wanted to do is that there is a second way of deriving a TOR, and I don't know how to explain this to you in like 30 seconds. But the point is that if you go back to the collisional model, I think I went super long, but like if you go back to the picture that we analyzed in detail, okay, and you basically take the limit where the collision time becomes extremely small, okay, tau, but the interaction strength rescales appropriately as the 1/square root of tau, so becomes ultra strong coupling regime, okay? Then you basically can obtain that the evolution, okay, becomes a Lindblad-Master equation, okay? And well, essentially, if you then measure just the environment, okay, then you are essentially doing a microscopic derivation of a mod like a Lindblad model without the Bohr-Markov secular approximation, actually in a totally completely different regime, okay, where you keep track, by keeping track of which ancilla has observed the jump, okay, in a certain amount of time, then you basically keep track of the heat, okay, and the final point being that, and I'm sorry if I didn't manage to arrive there, but I think it's better like not to overcome you with information. The point being that if you then have a Lindblad-Master equation, okay, then in some sense you can do a deformation like in the same way as Gabriel did last time with classical Markov chains, okay? You do a deformation of the Lindblad operators and of the Hamiltonian appearing in the Lindblad-Master equation, and you use Kramer-Rao bound onto that deformation to basically derive, you can derive a TUR, okay? Just straight from all these kind of like passages. So basically collisional model that we have considered, like repeated interaction scheme, you basically go to the continuum limit where in a very short amount of time, a lot of collisions happen and they're very, very, very fast, okay? And then you have a certain probability that in a certain window of time t, then you have observed one jump or no jump. Okay, this is the unravel of the Lindblad-Master equation that Anya presented, but derived in a slightly different way. Okay, stemming exactly from taking the limit of what we have observed. Everything is in the notes. But the point is, I'm just writing here stuff that you will arrive at a master equation for the system, which is in Lindblad form. Okay, so it's going to be the commutator with H plus a dissipator, okay, which is going to be sum over some channels of some rates times the Lindblad operators. Okay. And if you then kind of introduce an appropriate deformation of this, meaning that you basically move to an h theta, like theta is a parameter like kind of like measures this deformation strength, which is 1 plus theta h, and also the Lindblad operator Lk becomes something, if I don't misremember, something like Lk of t times L, where these Lk of t are this weird looking thing. Which I know it's like, why the hell would anyone want to consider this? Like, how did they come up with this? There's a reason, but it's more of as Gabriel said, it's more of an art to come up with this kind of deformation. And the reason was that if you consider this deformation, then the Fisher information can be seen to majorize the entropy production. Then you arrive at the final result, which has this form. So the variance of any kind of observable of the path, okay, of the Lindblad-Master equation divided by the average square is going to be greater or equal than something like 2 plus 1 plus a function, okay, times the entropy production average plus a term. And okay, let's leave aside, and with this I conclude this what this term means. It's a sort of like difference in average current, but this is the entropy production, and this is the only term you obtain if you kind of like neglect any coherences, any quantum coherences, and therefore this term becomes like an effect, like a correction purely induced by having coherences in the Lindblad-Master equation. Okay, so this is a result that I would send you like all the notes, and well, I'm sorry like if I had to run a little bit at the very end, but if you have any question, otherwise I thank you for for your time.
Some short questions. Otherwise, also over lunch, maybe.
Yes, yes.
So let's go for lunch. And we meet back at 1:30, right? Or should we shift it?